And then I'm going to share my screen. And let's just me announce this announcement again. Test 3 is Wednesday, 12/2. That is the first Wednesday after Thanksgiving break. I just want to make sure that's in the recording in case I need to look it up to confirm. So let's go down to my PowerPoint presentation. It's actually Pearson's, but I adjusted it. So we are going to talk about the broader topic called integration. So let's start the slideshow, play it from the start. So chapter 4, integration. So we've done differentiation. We are now going to be given a derivative and want to find that original function. So what's the objective in this section? The objective is to find an antiderivative of a function. Also, evaluate indefinite integrals using basic rules of anti-differentiation, and then use an initial conditions to determine an antiderivative. So that is what we are going to do. Those are our objectives. So taking a look at theorem 1 here. This d dx notation means we're given a derivative. We have a derivative. The antiderivative of little f of x. Okay, this little f. That's the f of x that we've been using given to us in many of our problems in the past. So this is the derivative of a particular function here. And we want to find its antiderivative. And I'm not too fond of how they've written this, so I'm not going to get into this notation here because I think we've got a better way of doing this when we go through what I have prepared for today. And we will talk about this constant C called the constant of integration. Now, these are basic integration formulas. You probably want to write these down or get the PowerPoint in MyLab Math and refer to them. I've shortened their PowerPoint quite a bit here because I'd rather present particular problems and us look at those problems that are like problems you would see in MyLab Math. So the first one I want to do today is, and I actually want to stop this for the time being, and I want to look at some antiderivatives. So let's look at an antiderivative. So when we write this notation, whoops, that's not what I wanted. I want this. When we write an antiderivative, that integral sign, that elongated S, if you will, stands for find all antiderivatives of. So let's say I want to find all antiderivatives of the number 1. And I want to do so with respect to x. So x is going to be the independent variable. So can anyone tell me, here's the big question of the day. Can anyone tell me which function, and we're looking for f of x, the original function. Can anyone tell me which function has a derivative of 1? What function have we seen that has a derivative of 1? F of x equals what? What function has a derivative of 1? X squared, 3x, ln of x, e to the x. What function has a derivative of 1? It would be x. Now, it could be x plus 1. It could be x minus 500. It could be x plus 5 million. We don't know. So we write this down as x plus a constant of integration like that to denote that there's infinite number of possibilities for an antiderivative of 1. If we go backwards and I look at this side, so I anti-differentiated to get this. Now, if we take the derivative of this side, what do we get? The derivative of x is 1. The derivative of this additive constant. This additive constant can be any real number between negative infinity and positive infinity. So we really can generate an infinite number of these answers. We could have x plus 5 million, x minus 20,000, x, equals the number e, not x, sorry. We could have the c. We could have the constant of integration equal to all of those numbers, negative 1,000, positive 1 million. We could have c equal the number e. We could have c equal the number pi. We could generate an infinite number of those. And by writing this antiderivative, this is how we write antiderivatives, this elongated s, it's called the integral sign. By writing our integration like this, the integral of 1 dx, we have to say that's equal to x, first of all, plus the constant of integration, where that constant, you can generate an infinite number of x plus this, x plus that, x plus something else, x plus yet something else. You can generate an infinite number of those. Now, if I want to go backwards, so this side, this way is called integration. This right here, integration. If we start on this side and go backwards, that's called differentiation. That's what we've been doing. If we go this direction. The derivative of x is 1, check, plus the derivative of an additive constant is 0. The derivative of any additive constant, any real number, is 0. So we have to include them all because x plus 0 is, or the derivative of x is 1. So if I want to differentiate this, let me just write it down so we're all clear and on the same page here. X plus c. If I want to differentiate that, let me see if I can make this go over here a little bit. There. If I want to differentiate that, the derivative of x is 1. The derivative of any additive constant, any additive real number that I'm adding, and don't forget that subtraction is also adding a negative. So the derivative of x is 1, plus the derivative of this constant is 0. The derivative of any additive constant is 0, so I just get 1. And what you'll notice is 1 is in this first position here. And that is, so we have that integrand. That 1 is actually an integrand. That integrand is 1. This just tells us what we're integrating with respect to the variable x. If we were integrating with respect to the variable t, we'd have a t here instead of an x. So we can go both ways here. We can anti-differentiate, which would be also called integration, would be going in this direction. We can go to this side, and then we can differentiate and go to go this direction, which is what we did here. We differentiated. The derivative of x is 1 plus the derivative of the constant is 0. So they're really, in some sense, reverse processes of each other. Now, this one isn't in the slide. That's why I wrote it in. This one is not in the slides. And I think it's really important because this does come up where you've got a 1 here. And also what comes up is this. The integral of dx, just dx, like that. And if that comes up, that there's an understood 1 that here. So you might want to write this down across the top. You don't need to write this arrow here, but this is not in the slideshow presentation. And so I wanted to make it clear to everyone what you would do in the case if you just saw an indefinite integral of dx, and what you would do in the case if you just saw an indefinite integral of 1 dx. They're both equal to x, or whatever your variable is, plus the constant of integration. So let's go on. Anybody have any questions at any time, please stop me. So we have here in there 1 in the slideshow presentation. And then let's go back to the slideshow presentation, and we want to do it from the, let's see what I'm looking from the, over here, custom show. Let's see what I want. Rehearse, I don't want that. Maybe it's the one up here, play from the current slide. It's interesting, they've got 2 places where they say slideshow. Okay, so now we want to look at this anti-differentiation rule. So this right here is called an integral sign, this elongated S. And this is saying now we want to integrate a constant, like the number 1 or the number 2 or the number 3 or so forth. And what do? We're going backwards now. So if we had like the number 4 here, for example, and there I go, I want to go back to, I think we might just leave it in the other mode there so we can take a look at this. So if I put, say, a 4 here for k, and we want to integrate 4 dx, we're looking for the original function whose derivative is 4. So if we had 4x over here, would that be the answer? And the answer is yes, because what happens if we take this side and differentiate to see if we actually get this over here? So the derivative of 4x is this number multiplier 4 times the derivative of x, which is 1. 4 times 1 is 4, and that's exactly what we have here. This dx is just telling us what we want to, what variable we're using. And then plus, we need this constant of integration, plus this additive constant, whatever it is. It could be an infinite, we have an infinite number of these answers. We have 1 for every single different real number for that constant of integration. We have millions and millions and billions of these that we can be generated. So we have to include them all in that one constant of integration where C is any, we have to have one of these 4 x's here. We have to have one of these constant for each real number. And then we have to generate, we can generate an infinite number of those. So it's just real important to understand that I could spend the rest of my life writing down 4x plus a real number, and then comma 4x plus another real number, and then comma 4x plus yet another real number. I could spend my whole life doing that and I still wouldn't be done doing it. So that's just something to keep in mind. So there's this interplay where you can go back and forth with integration and anti-differentiation. So when we have this elongated S, there are no numbers here. There will be a number down here shortly in the next section, and a number up here in the next section, and then we'll have what we call a definite, has indefinite D. It may sound like I'm saying indefinite, so I want to just point out, when you have an A down here and a B here, we are going to look at those kinds of integrals. Those aren't called indefinite like this is. Those are called definite integrals, and they actually represent an area. It's quite amazing. So we can do this we put in 4 for k here. We can do this same routine here for any real number. So next, we've got the power rule. That's what we really have here. If we were asked to differentiate x to a power, it would look like x to a power. It could be x to the p, x to the r, whatever. But we're anti-differentiating, so we want to look at it even differently. So when we differentiate x to a power, we subtract 1 from the exponent. So now that we go backwards, it makes sense that we're going to add 1 to the exponent. However, it's not just enough to write x to the r plus 1 in this case, because if we check this, we're going to get r plus 1 times x to the r, because we're going to subtract 1, and we'll have an r plus 1 down front, but we don't have it down front here. So that's why we have to compensate by dividing by r plus 1. So if I were to differentiate this to check this right here, that derivative would be r plus 1 times x. And then we take the old exponent, r plus 1, and subtract 1. We're just going to get r. Now, this isn't what we have. We have the x to the r here, but we don't have the r plus 1 here. We're trying to, and so we know we need to do something else. And that something else is we have to divide by r plus 1. Because if we divide by r plus 1, this will cancel this, and then we will have just x to the r. And I better erase this because I don't want you all to think that I'm crossing that out for good. I just wanted to show you how it cancels here with that. So let me just take care of that. I'll go get the eraser and erase this and clean this up. So when we anti-differentiate, we add 1 to the exponent and we divide by that same exponent. And they're telling us, provided that r cannot be equal to -1. If r is equal to -1, we just kind of sneak in a -1 there for r. -1 plus 1 is 0. And division by 0 is undefined. That's why r cannot be equal to -1. When the r is equal to -1, there is a different rule that applies. Okay, any questions so far? So let's go on, and we'll see all of these rules in action shortly. We'll look at the homework. Now, I did not like the way they wrote down rule number 4. So I wrote down rule number 4 differently for our purposes. See, this reason why I did this is because it turns out that there's this number multiplier in front, and you can actually write that down before the integral sign. And that's why I did that. So rule number 4, what do you do if you want to find all antiderivatives of e to a power, where in that power you've got a number a times x? And of course, we're integrating with respect to x. Now, we all know that the derivative of e to a power involves e to that power. When we go backwards, it makes sense that the all antiderivatives would also work like that, if we want to find the all antiderivatives of e to a power, it makes sense that we're going to copy over e to that power. But we have to be careful here because we need to compensate when necessary. If I just differentiated e to the ax, if I went backwards, I would get e to the ax times, or what? Not times, but divided by. So let's look at this. If I write this, let's make sure we're all on the same page. If I write this, f of x equals e to the ax. And now I want to find its derivative, f prime. So what is that equal to? That's equal to e to the ax times a, right? So that's equal to e to the ax times a. Times the coefficient there, times a. Wait a second, let me think of this. So if it would be, yes, it's e to the a times a. Okay. Any questions on that? So if I go backwards, it's a little different because we have to be able to go in both directions and get the correct answer. So what turns out to happen in the case of anti-differentiation is when we want to find all antiderivatives of this integral here, e to the ax dx, it is equal to e to the a raised to the ax. We still copy that over, but this time we don't multiply, we divide by a. We divide by a. And then we add our constant of integration. So a couple moments ago, I talked about what happens if you get a negative, if you have x to the r, where r is -1. So we have x to the -1. So let's look at what happens there. So if we're integrating x to the -1 dx, we're looking for the function, and we're looking for a special function, but let's go through this here. This x to the -1, we could bring the x down to the denominator. And if we bring that x to the -1 down to the denominator, the only thing that's going to change is the sign on the exponent. So the integral of x to the -1, and you will see it written like that, dx equals, all I'm doing here, or this that they did here, is they just did algebra, used a property of exponents to bring this x to the -1 down to the denominator. And all that's going to happen is we're going to change the sign on the exponent. So the x comes down and this -1 becomes a +1, but we don't have to write it in. And then that's times dx. That's telling us what variable to integrate with respect to. And then this is equal to the integral of 1 times dx, which is dx over x. Now, I probably wouldn't use it in that form. I'd probably just ignore this. We don't generally use it in that form, but you might see it written like that. I don't remember seeing it when I looked at the homework. And so we're looking for the original function whose derivative is 1 over x. And that is ln of absolute value of x plus a constant. So I wouldn't use this form. I would always just, because I would always use the absolute value sign. I would always use the absolute value sign. Yeah, I'm going to get rid of that. I would just use this form right here. This is this one you want to use. That way you don't have to worry about, be concerned about cases. And I believe it's on the formula sheet like that. Let's just take a quick peek at the formula sheet for a moment. We have got actually, I think what I did there is, let me see. I had the formula sheet up and I said, oh no, we're not going to use it. And I need to look at these documents here. And let's look at survey of calculus. And let me see if I can, yeah, okay. So we've got this ln of f of x equals that. So we don't have, and this brings up a very good point, and I kept thinking about it, and each time I thought about it, I didn't state it, but the antiderivative rules are not on the formula sheet. So you will need to know them. So I wanted to check the formula sheet there, and let's go back over here. So this is the one I would use here. That's going to keep you safe. That's the one I would use. So let's go on. And I think you're going to see these in action. So that'll be, I hope that you learn them and feel more comfortable with these rules as we go throughout our class. So there's a couple other properties we need to look at that are important just to talk about before we get started looking at some of the problems. And remember, in some sense, integration is the reverse of differentiation. However, when we integrate, we have to add on that constant of integration all the time when we have an indefinite integral like we're dealing with right now. So when we differentiate and we have a number, say we have a function, a function, and let's say we've got 3 times x squared. And we want to differentiate. We write down the number multiplier and take the derivative of the rest. When we go backwards, this is a number multiplier right here. There's a multiplication sign understood to be in there. Okay. So we write down the c and take all antiderivatives of the rest. The same thing. That's why this c comes out in front of the integral sign. We just take the c and move it out front. It's really what we're doing when we differentiate. We write down this number 3 over here and take the derivative of the rest. When we integrate, if this were the number, let's say 3 over here, we could write the 3 outside of the integral sign and then find all antiderivatives of what's left, which would be this function that we're calling f of x. Same really, it makes sense because we're going back and forth. We're doing the reverse processes. Down here, it's just saying when we differentiate, we know that if we differentiate as sum, that's just the sum of, so that's just the sum of the derivatives. And if we have a difference, that's just the difference of the derivatives. And that's all we're really doing here. We're saying, okay, if we have plus sign, we can find the integral of f of x and then turn right around and add it to the integral of g of x. And if we have the integral of f of x minus g of x, we can first find the integral of f of x and then subtract off the integral of g of x over here. So let's just restate these according to how they're stated in the slides. In the first property, property number 1, the integral, that's this sign right here, of a constant, that's c, times a function, which is this f of x here, is the constant, which means you can bring it out front, times the integral of the function. And that would be here, the constant. They say that the integral of a constant function is the constant right here times a function. Sorry, times a function. I think the phone's going off. I'm sorry about that. So it's yeah, it's still going off. Just, I'm sorry about that. I could run out and get it, but I think it's just, okay. Let me go get it. I'm going to turn it off. I'll be right back. Sorry about that. Lesson learned here. I'm going to just have to have that part of my routine, standard routine, to make long list of things to do here. So if I reread this again, the integral of a constant, okay, times a function is the constant, which means you can take this constant out in front, and that constant c is like 5 million or negative 600,000 or whatever. You could bring it out front. Has to be a constant multiplier to do that, though. So the integral of a constant times a function is that constant times the integral, which is this sign, of the function. So the integral of function would be all of this. So all that's saying is you can bring this constant multiplier out front and then just write it down and then integrate. You bring the constant multiplier down front and then integrate what's left. Of course, carrying along the constant multiplier. And down here, all they're saying in words, their words, the integral of a sum or difference is the sum or difference of the integrals. So this is all important terminology and rules that you need to know. Unfortunately, they are not on the formula sheet. So let's take a look at some problems here. Let's go into the 4.1 homework. So I want to emphasize that what we're talking about today are indefinite integrals. So find the indefinite integral, and each indefinite integral you will need to write down this constant of integration at the very end. This additive constant of integration, because you can generate an infinite number of these. There's 13x plus a real number, 13x plus another real number, 13x plus yet another real number. You can generate them forever and ever and ever. And so we just put on one big constant of integration to indicate that. As opposed to what we are going to look at on Wednesday, these definite integrals. And you can see that we've got a number that's down here, this is 0, and a number up here, this 4. And these have to do with areas. And you can see that I've got some graphs drawn that look like I'm finding the area. And that is exactly what we're going to be doing on Wednesday. So let's go back here. So find the indefinite integral. In other words, that the A and the B that we were looking at before, those numbers there, those are the limits of integration. These are called definite integrals. These are called indefinite integrals. So find the indefinite integral of 13 dx. This just tells us we're integrating with respect to x, which is very important because we've got to write down 13 times whatever variable we're talking about. If we didn't have a dx here, we wouldn't know what variable we were talking about. So what we're looking for here when we integrate is we're given this 13 here. That 13 is the derivative of some function. We want to find that function. So we're going in reverse. We're going to ask ourselves, how do we do this? So let's take a look at this. And what I would do, I mean, personally, this is one way to approach this problem. I would write this as, I would do what the PowerPoint suggested to do. I would bring that number multiplier. There's an understood multiplication symbol between 13 and dx. I would bring that number, that multiplier out front. I would put this 13 right here. That's going to leave a 1 inside though, times dx. And all this tells us is what variable are we integrating with respect to. So now the reason why I like to do that is because I now need to think about, well, first of all, let's copy over that 13. We now need to think about which function, which f of x has a derivative equal to 1. Which function has a derivative equal to 1? That would be x. And then because we are looking at an indefinite integral, we're going to add on the constant of integration. And that is the answer. I prefer to do it like this and just remember what the antiderivative of 1 is. It is x. The derivative of x is 1. Any questions on this? And this capital C is called the constant of integration. Now, a few moments ago, we looked at what was upcoming, and we saw that those areas, when we are looking at definite integrals, we are finding areas, and we're going to just get numbers, a number for the answer, because we're finding an area. And I bet you're all wondering how this all relates together. So well, we will talk about that. So let's go on. Does anybody have any questions on problem number 1? Let's take a look at problem number 2. So what are we doing here? We want to find the integral of x to the 4th dx. So how do we do that? We think power rule. If we don't have a number, we haven't understood 1 there, so we don't have to bring anything out from front of the integral sign. When we integrate, we're going backwards. So when we differentiate, we subtract 1. When we go backwards, we add 1 when we're talking about the power rule. So this x to the 4th becomes x to the 4th plus 1, which is x to the 5th. But we have to compensate, because if we didn't compensate, we would be talking about this. And if we wanted to find the derivative of that, what would we get? We would get 5x to the 4th. And that's what that derivative here would be equal to. Let me make sure that big derivative notation there. We don't have 5x to the 4th. We have just x to the 4th over here. So that's the reason why we have to divide by this power here. Divide by this power 5. So the power rule for anti-differentiation tells us to add 1 to the exponent and divide by that very same exponent. And then add a constant of integration, add the constant of integration. So this is x to the 5th divided by 5 plus the constant integration. That's the answer. Any questions on that? So if you want to take some screenshots of those screens in the PowerPoint, you can do that, and we can do that in a little bit later. So let's look at number 3. So number 3, evaluate, which means find the value of the integral of x raised to the 6/7. So how do we integrate that? We're finding all antiderivatives. We have x to a power. When we integrate, we add 1 to that exponent. So we have x to the 6/7 plus 1. Now, the other step that we have to do is divide by that same exponent, 6/7 plus 1, and add our constant of integration. And it looks like I forgot to put it in here. Want to make sure you're writing in those constants of integration on test 3, which is on the 2nd of December. It's the first Wednesday after Thanksgiving break. So 6/7 plus 7/7 is 13/7. We divide by 13/7. Add a constant of integration. We now we have a complex fraction here. So I am getting a low quality internet, but it seems to have gone away. So hopefully I'll keep my fingers crossed. So we've got this. We've got a complex fraction. So we need to do this process, invert and multiply. We need to bring this deal with this 13/7. So we're going to flip this over and get 7/13 and move it to the numerator. And add on our constant of integration. Now we write this number multiplier here, we want to write out front that standard 7/13 x to the 13/7 plus constant of integration. Now you can check every single one of your answers. If I check, let's go ahead and check this. I'm going to take, now we remember we anti-differentiated. So this is the original function. This is the original function at this point. We could call this, let me figure out here what I want to do. Yeah, let me and I'll get rid of this. Okay. So this is what we're doing now is we really have a function here. This right here is a function. We could call it f of x. This is our original function. How can we check? We can just differentiate this function. So we went backwards to anti-differentiate to get our. Now to check your work, you want to take your original function, take the derivative, and see if you get this integrand right here. That's what we want. So if we differentiate here, we write down that 7 over 13. So let's write down the 7 over 13. Oops. Having a little, I don't remember exactly how to do this. Let me see if I can do it. Okay, I think I can handle this now. So we get x, we've got our function, we wanted our original function, we want to differentiate and see what happens. And so we're going to differentiate this. So we don't want this, we want to write down 7/13. And I think I've got it. 7/13. That's the number multiplier. Let's write it down and take the derivative of the rest. What's the rest? This is part of the rest. So now we've got to differentiate x to a power. That 13 over 7 comes down front. And then we have to write down our x. And then we have to take our old exponent here, 13/7. No, we're bringing that down front. And what do we have to do? We have to take that old exponent and subtract 1 from it. And plus the derivative of that additive constant. And that, we got a little streak right there. That's supposed to be 7. And now that's going to be hard to fix, but let me just get it fixed. So this is going to be 13. Oops. I know maybe what I'll try to do here is see, let's see if I can just write over it with red or something like that. So this is 13/7. Okay. So this 7 divided by 7 is 1. This 13 divided by 13 is 1. We have x, and we want to take this exponent here and subtract 1 from it. So this should be this is a subtracting 1. So if I take my graphing calculator and I do that, I'm going to get 13 divided by 7 minus 1 math bracket, and I get 6/7. I get this right here, 6/7. So this here turns out to be 6/7. Even though the minus 1's up a little bit, turns out to be 6/7. So I really want to encourage you all to check yours. Any questions on problem number 3. So we'll look at some more. If you aren't feeling super comfortable with this yet, that's okay. So let's not look at 4, let's look at 5. So number 5, we want to find this integral right here. I think I'm going to close this. Yeah. So what I did is remember that you can bring out number multipliers out in front, and you can also split integrals. If you're integrating terms, you can integrate term by term, just like you can differentiate term by term. Terms are added. So I'm going to look at this first term here. In that term, we have a number multiplier. So I brought that 6 out in front. I wrote down the integral sign, and inside what's left is x squared for that first term only. And then every integral has to have a dx with it, or a dt, or whatever you're talking about. Then this minus is really -1. So I brought the minus sign out in front, and this 6 out in front, because those are numbers. And then an integral sign, and this time we have x here, which is really x to the first. And then each integral sign, each one of these integral signs has to have a dx. And then we have plus, so we've got a plus sign here. The integral of 3. And then we need a dx. So we're really integrating this, breaking it down so that it just makes more sense. So here I just copy down the 6. This is x to a power. So when we integrate x to a power, what we do, and I will say this is a simple power, because the base is just x. But when we integrate, we add 1 to the exponent. So this is x, 2 plus 1 is 3, and then we have to divide by that new exponent to compensate. And then -6. If we integrate this, it's x to the 1 plus 1, which is 1 plus 1 is 2, so it's x squared. And then we divide by that new exponent of 2. Plus 3. Okay, I could bring this 3 out front. There's an understood 1 left. This is 3 times 1, so there's an understood 1 left. So we can write down the 3, and we need to ask ourselves, what function has a derivative of 1? That would be x. And then we want to add on the constant of integration, because we have an indefinite integral. And then we just need to clean everything up. 6 divided by 3 is 2. And then x cubed. -6 divided by 2, 3. Plus 3x plus our constant of integration. Anyone have any questions on that on number 5? So let's do one of these. I just want to remind you, if you want to bring this x to the 5th up from the denominator, it comes up to the numerator as x to the -5. The only thing that changes is the sign on the exponent. And then what I did, let's go ahead and do this. Then what is we just have to integrate x to a power. So it's x to that power. It's x to that power, and when we integrate, we add 1. It's the reverse of differentiation. But then we have to compensate by dividing by that new exponent, which is -5 plus 1. And of course, plus our constant. And then you do -5 plus 1 is -4. You'll get this -4 in the denominator as well, since this is the same as this, and the constant of integration. And you could leave it like this. I just wrote another step so I can make sure I got their correct answer. Looking at number 7 here, this 8 is in that little v of the root. So this is really asking us to integrate the 8th root of x dx. Well, a root like that is just an exponent. It's not x to the 8th. If we wanted that, we would write it down as x to the 8th. It's actually x to the 1 over this index of 8 here. So I don't want to go ahead and do that. I'm going to leave that to you. I just wanted to remind you all that if you've got an nth root of x, that is equal to the radicand, which is x, to the 1 over whatever index you're talking about. So that one's similar. You just bring this up to the numerator as x to the -9th and go there from there. So let's take a look at this right here. We want to find the integral of 12 divided by x. The first thing I'm going to do that I did is bring the 12 out front because it's a number multiplier. Then that 12 is really 12 times 1. So there's really a 1 here over x. Now 1 over x, our rule. What did it tell us that our rule, what did our rule tell us? Oops. What did our rule tell us? If we want to integrate x to the -1, well, that x to the -1 is really 1 over x, like this. 1 over x to the +1. So that's what we really have. So that is ln of the absolute value of x plus a constant. Like that. So you might want to jot down, I rewrote this rule over here. You might want to jot down this rule. It's a really good rule to have. Wait a second. Wait. Let me rephrase that. Let me write down the rule. This I was showing. Sorry about that. I was showing something else here. Let's see if I can erase that. Yeah, I want to erase that. I don't. I'll write it down for y'all so you can see it. Yeah, I don't want to circle this. I think what I was showing there is why it's important that we use the rule that involves the ln of the absolute value of x, because what you'll notice here is we have, if we were to bring this x up to the numerator, we'd get x to the -1. And also, you want to see that if you have an x in the denominator, here, you bring it up as x to the -1, it's not going to work for you because you're going to ultimately get division by 0. So if I look at it here, if the integral of 1 over x dx equals, I'll bring up this x to the to the numerator, but there's an x to the first down here, so it comes up as x to the -1 dx. If I take and add 1 to the exponent up here, like the power rule, we would get -1, add 1 to the exponent, divide by that new exponent, we're going to get division by 0. So we cannot use the power rule for this example. We really need to use another rule. So whenever you have x to the -1 like that, or you could just look at it as 1 over x if you want to, you have to use a different rule. And here we are going to use the rule that involves the natural logarithm. So here, the integral of 1 over x, this guy right here, is ln of absolute value of x plus a constant of integration. So this guy up here, just in general, is the integral, I'm going to write this down so you can see, of 1 over x dx is equal to the ln of the absolute value of x plus a constant of integration. So if we look at this one, that 12 comes out in front of the integral sign because it's a number multiplier. There's still an understood 1 up here, though. There's still an understood 1 there. So that's the integral of 1 over x dx. That means we have to find, when we bring that 12 out in front here, we have the integral of 1 over x dx. And so that's equal to the 12. You write it down again. This integral right here is equal to the ln of absolute value of x plus the constant of integration. And we always just add the constant of integration on at the very end. Any questions on number 9? So I'll do a little bit of this one. I don't think I want to do too much of it, but if you have such an integral like this, what do we want to do is the question. So we want to break it in 2 because we have a difference. Difference is just adding a negative. So we want to find the integral of 7 divided by x dx. And then this minus can go out front because it's a -1 and number multipliers can go out front. And then we want to find the integral of 4 divided by x to the 5th dx. So this number multiplier 7 can come out front down on the normal line of writing. And we just have a 1 left here, 1 over x dx. And then this minus sign, this 4 can come out front because it's a number multiplier. The integral of, if you bring this up, all that's going to change is the sign on the exponent. So we get x to the -5, the numerator, dx, because every integral sign has to have a dx or a dt or a d something. So this one is just 7 times the integral of 1 over x. We just looked at that. The integral of 1 over x is ln of the absolute value of x. We do not add our constant of integration until the very end. So that's just this derivative of this term here is just 7, and this integral 1 over x dx is just ln of the absolute value of x. So we get 7 ln of absolute value of x minus 4. We can use the power rule here because our entire integrand in here, except for the dx, is everything in here except for the dx is called the integrand. this x to the negative fifth. This is the integral sign. So, and all we have to do to integrate x to a power is take that x, add 1 to the power, and divide by that new power. And we add our constant of integration always on at the very, very end. And so it's just a matter of cleaning this up. We have a, if you notice, we're going to get a negative 5 plus 1 is negative 4 in the denominator. That negative 4 will and this will be negative 4 divided by negative 4. That will give us a positive 1. Okay? And then we have a negative 4 in the exponent, so we're going to move that to the denominator and change that to a positive 4. So we get x to the fourth in the denominator plus the constant of integration. So you will have to simplify these expressions. So let's take a look at e to a power. We have not looked at e to a power yet. So if we want to find the integral of f of x dx, which is in this problem, which is equal to blank, we start off by putting in e to the negative 2x for f of x. And we get the integral of e to the negative 2x dx. Now when we differentiate e to a power, we just write it down. Same when we integrate. So if we copy over e to the negative 2x, and we're in the process of integration, so we don't want to put in the integral signs. You want to use correct notation on the test 3 and the comprehensive final for full credit. So I copy over this e to the negative 2x, and then we have to divide by the derivative, or you could say the coefficient, if you will. Either the derivative of this power you could use, or the coefficient, which is negative 2. You have to divide by it to compensate. And then you want to add on your constant of integration. And that should be good enough here. I just wrote there's a understood 1 here, so I wrote negative 1 over 2 out front, e to the negative 2x here, plus a constant of integration to make sure my answer looked exactly like theirs. So you can, once you anti-differentiate and you clean it up, like if you want to do any additions and so forth, like you want to definitely clean this up, negative 5 plus 1. Okay, let's take a look. Let's not do 12. Let's take a look at 13. So 13, we want to integrate 2 times e to the negative 0.4 x dx. That 2 is a number multiplier, so I would encourage you to bring it out front to get it out of the way. And then copy over this integral sign. This integrand here is e to the negative 0.4x. And then we have to keep our dx. So we want to then copy over our 2. If we want to integrate e to a power, it is e to that power copied over, divided by the derivative of the power, which would be just negative 0.4 times the derivative of x, which is 1. So it's negative 0.4 plus a constant of integration. To get their answer, all I did was take 2 and divide it by 0.4 on my graphing calculator and put the negative sign out in front, and then wrote down e to this power and added the constant of integration. Any questions? So let's talk about this. If you see something like this, you can multiply this out. This means you take 2 of the base 9x plus 5 and multiply them together. So you can see 9x plus 5 times 9x plus 5. And then I went through that process. I think we've talked about how to handle that today. So I think, I want to do one of these problems for you, but this one isn't too interesting. Let's see what our other options are. So let's take a look at this one. So we're almost done, but I'm just going to take a look at one of these for you in the time that we have remaining. Find f such that the first derivative, that prime means first derivative as a gentle reminder, find f such that its derivative is x squared plus 5, and that f, not f prime, but f function at x equals 0, okay? And that all of this is the y. So what's in the parentheses is the x. So what I'm going to start by doing is, since we have information what happens with the original function, we have a condition here. We're going to start with the derivative and integrate. We're going to find all antiderivatives of the derivative. So we're going to write down the integral x squared plus 5. This is the derivative inside in the integrand dx. So if we want it, we can integrate term by term. You don't have to break it apart if you don't want to. The integral of all antiderivatives of x squared, we add 1 to the exponent, divide by that new exponent. And then we have a plus sign. And then we write down the 5, and there's really a understood 1 here. There's really an understood number 1 here. And let me just put in a 1, like that. So I wrote down the 5, and then we need to deal with this 1. So which function has a derivative equal to 1? That would be x. And then we add the constant of integration. Now, very important that we write down that this integral is equal to the original function f of x. Very important to use this notation because it's actually quite helpful. I might have glossed over that, but we want to know in the context of this problem whether this is our f prime of x or whether this is our f of x. It is our f of x. When we differentiate, we're getting back our original function. So we are told that we have this condition here. This in parentheses right here is our x. That 0 is our x. So what are we going to do? So that 0 is our x. So we're told that our x is 0. And that means our f of x or our y, when x is 0, our f of 0 equals 7. So that stands for y. So this is a y coordinate right here. This is our y. That is our y. Just so everybody's clear. That's our y. So what are we going to do? So our 7 is our y. No. Now keep in mind what we found all along here. This f of x is our y. So we want to take out f of x. And in this case, it's going to be f of 0. Okay. So we want to take out this x and put it 0 in its place. So we want f of 0 in a single, not equal to what's up here, but separate. So this f of x, this f of x, the entire f of x, we want to replace it by 7. And I'm sorry if that looks like an exponent. I didn't mean it to make an x look like an exponent there. So this entire f of x is 7. You can even see that. That looks like f of x where x is equal to 0. So I take out f of x, put in 7, make it equal to f of 0. And what does that tell me? I now have you could call this an equation if you wanted to. So I want to focus on this part right here and this part. Okay, I want to focus on this part and this part. And I'm going over a little bit, I apologize. So let me I'll wrap it up here. So that's 7. This 7 right here is equal to f of 0. That's what I'm told. So I'm using my condition here. And then where can I put that? I can put this into, this is my f function. So I can put 0 into my f. I can take this 0, put it into using my f function, and this 0 is actually the x. So I can put this 0 in for x here and here. If I do that, I get 0 cubed over 3 plus 5 times, putting in the 0 for x, 5 times 0, plus this constant of integration. Now, what this condition is going to tell us is what is that one special constant of integration that we want to use. Very helpful to businesses. So I'm going to solve this. We're going to solve this. This is 7 equals, this is 0, this term is 0, and this term here is just plus the constant. So what we actually end up with is this cancels because it's just 0. This cancels because it's just 0. And we end up with 7 equaling C. So our C is 7. So we want for our answer all of this where we're just plugging in 7 for the constant of integration. So this is just getting plugged in right here, right there, for this one special scenario. And it's really important because this is how businesses make use of anti-differentiation. So we get x cubed over 3 plus 5x plus 7's going in for C here. Now, you're not always going to have a super nice condition here. Sometimes you will and sometimes you won't. So any questions on that? And I didn't mean to keep you over. Up to you. Thank you. I owe you 4 minutes. Remember that the third test is on December 2nd. So bye for now. And let me wait a second. I've got to take attendance. So I'll take a quick screenshot here. Bye for now and stay safe. And I will see you on Wednesday. Take care, everybody. Bye for now. Feel free to exit the conference. I wish I had time to talk to you, but I don't really have any time. You can reach out to me via email if you need to. Bye for now. Bye, Manna. I'll see you later. I got to go set up my next meeting.